Hey there, geometers. Today we'll be looking at volume and surface area of prisms and cylinders, and we'll also be looking at similar solids. So to get started, we're going to look at this triangular prism that is shown here. I know it is a prism because it has a consistent height between the two bases, and the other requirement for a prism is that my bases are congruent. And if you look at the shaded triangular bases there, I can see that they're both the same size. It does not come to a point or an apex. That would be a pyramid. So we're going to be focusing on prisms today. All right, so let's get to it. The first thing I need to do is find the surface area. It may be helpful to draw the net of this shape. So I'm going to envision kind of opening up the top triangle and then kind of unwrapping the three sides. So then this side over here can be drawn here. This side here matches up. And then I know the height of my shape is still 9. Now, as I look at this, it's really just some rectangles. And specifically, I know the length of this rectangle matches up with this side of the triangle. And then the length of this rectangle would match up with the length of this side of the triangle. Now, special right triangles are going to help me out a lot here. This is a 3, 4, 5 triple. So now I can look at my net and say, well, it's just the area of the two triangles plus the area of that rectangle in between. Or if you looked at the video yesterday, you would have learned that surface area of a prism is 2 times the area of the base plus the perimeter of the base times the height. I can either draw the net or use that formula. Just remember that capital B stands for the area of the base. So then putting it together, I would have 2 times the area of the base plus the perimeter of the base, which would be this 3 plus 4 plus 5, or looking at my net, this 3 plus 4 plus 5, they're the same thing, times the height of the solid. So then simplifying that expression is going to give me 120 square centimeters for the surface area of that triangular prism. Let's take a look at the volume. My volume formula is going to be the area of one layer, or the area of the base, times how tall my solid is. Now remember, this capital B stands for the area of the base, not just the length of the base. So I know that that area of that triangle, that 3 by 4 triangle, was 6, and then I'm going to multiply that by the height, which is 9, giving me a volume of 54 cubic centimeters. The same formula that worked for rectangular prisms still works for triangular prisms. And then we can expand this idea to other prisms. In this case, this is a hexagonal prism where the base is a hexagon. So again, my volume, I need to find the area of one of those hexagons with an edge length 4, and then multiply that by the height of the solid. To look at the surface area, I would have the area of the hexagons plus this length here is going to match up to the perimeter of that hexagon, and then the height of the solid would be right here. So my surface area formula for a prism still applies here. 2 times the area of the base plus the perimeter of the base times the height. But because this is a hexagon, when I draw my central angle here and do 360 divided by 6, I know that that's 60 degrees, and then cutting it in half gives me a 30, 60, 90 triangle, which gives me some advantages to finding the area of one of those triangles. I know the apothem would then have to be 2 root 3 using my special triangles relationships. So then I'm going to go through and find the area of one of these triangles, isosceles triangles, and then multiply by 6. So my base is 4, my apothem is 2 root 3, the area of one triangle is 4 root 3, and then to find the area of the hexagon, I would take that times 6. Now this one worked out nicely. I could leave it in exact form to find my volume. The area of my base was 24 root 3. The height of my solid is 7, so when I find the volume, I could just multiply the 24 root 3 times 7, which would give me 168 root 3, or as a decimal approximation, 290.985 cubic inches. And now we've done most of the work. I have the area of the base. I can just go ahead and plug that in to solve for my surface area of this solid. I'm going to take 2 times the 24 root 3 for the hexagon, plus the perimeter of the hexagon. Well, each side was 4, so that would be 24 times the height of the solid, which is 7. Simplifying that expression would be 48 times the square root of 3 plus 168. This is a perfectly acceptable answer in exact form. I could also do approximate and put it to a decimal to the nearest thousandth. So again, it's nice to see that even though my base changed in my prism, my formulas still worked. I can still take the area of the base times the height for the volume, and the surface area I can take 2 times the area of the base plus the perimeter of the base times the height of the solid. But what about cylinders? Carter wonders, what if the bases are circular? If I look at this one, how can I find the surface area and the volume? Well, the volume I'm actually not too worried about. I'm still going to use that base times height formula. It's just that in this case, the base is a circle. So I would have to take the area of the circle, which is pi r squared, times the height of the solid or the cylinder. Now, even though I can leave this in exact form, I still should simplify it. I still need to multiply 25 times 8. And I still need my units on there. So volume doesn't change, I just have to find the area of the circle instead of doing my method for either a triangle or a hexagon or whatever the base is. Let's go back to this cylinder. Take a minute and find the surface area for this cylinder that is pictured here. All right, I want you to watch this animation closely. I'm gonna open up this cylinder and I'm gonna lay it flat. And as I open that up, the edge of the circle matches up perfectly with the edge of, or the length of that rectangle. So now let's talk formula. I still have 2 times the area of that base because I have 2 circles. And now I just need to figure out the dimensions of the rectangle. I know one of the sides of the rectangle is the height of the cylinder, and the other side has to match up to the distance around, or the circumference, of circle B. Another word for circumference is perimeter, so the area of that rectangle is the perimeter of the base times the height. It's the same formula as a prism. Now I can substitute in that the area of a circle is pi r squared and that the perimeter of a circle is 2 pi r and get a formula that's specific to a cylinder, but I don't need to. I could certainly just use the formula that is standard for a prism and then just recognize that the area of the circle, I can just replace the b with the pi r squared and the perimeter of the circle with 2 pi r. The last thing we're going to investigate is how a solid's volume changes as the scale factor changes. So I'm going to investigate, this is my original one here. It is a 1x3 rectangle that is 1 unit tall. So the area of the base is 3 times the height gives me a volume of just 3. If I don't change it, my volume stays the same and the ratio would be 1:1. For my scale factor of 2, that would be a 2x6. So now I would take the area of the base times 2, and I would get a new volume of 24. The original volume of the first one was still 3. That ratio is 24 to 3, or 8 to 1. Now I don't have a scale factor of 4 drawn here, but if I did, my dimensions would be 4 by 12 by 4, taking the original dimensions and multiply everything by 4, which would give me an area of 48 for the base, and then multiplied by 4 for the volume would give me a volume of 192. Now I'm looking for some patterns here, so I'm going to simplify these last two ratios. And now I'm going to look for a comparison between my scale factor and my new volume ratio. I go from 2 as my linear ratio to my volume ratio is 8. I go from 3 to 27 and 4 to 64. The ratio of my volumes is my original linear scale factor cubed. So we can add this to our list of ratios that we know for similar polygons, similar figures, now similar solids. If two figures have a linear ratio of r, we know their perimeter also has that same ratio. Their area has a ratio of r squared, and now I can add the volume ratio to that list. It is that ratio cubed. We will be using this and practicing this over the next few days in class. Use your newfound knowledge to answer the question below about volume ratios.